So here we go, October 2017 M1 IAL. The first question is basically a equilibrium or question. It's talking about something being dragged along at constant speed, which means A equals 0 or the forces are balanced. So it's like an equilibrium question. Equilibrium means constant velocity or stationary. Acceleration is 0. So okay, so we've got something being dragged along by a strap, okay, and the tension in the strap is 20 degrees to the horizontal. Let's mark on the forces. There's a reaction force here, there's a weight, which is 40 G, because it's 40 kilograms, and because it's moving, we know that F equals to mu r, so we can say it's 3/4 r, because we're given that mu is 3/4. Okay, so right, we're going to resolve vertically. So we've got the r going upwards. We've got the component of the tension going upwards, and that's going to be T sine 20, because the angle is 20 is away from it's the kind of not next to the marked angle there, so it's T sine 20. So that's plus T sine 20, and that's equal to the weight, so those are both going up, equals to the weight, which is 40 G. Right, so that was my resolving vertically equation. Now let's resolve horizontally. So we're looking at horizontal components. The component of T is T cos 20, because it's next to the marked angle 20 degrees, T cos 20 there. So that's T cos 20 equals to 3/4 r. Those are balanced out. The T cos 20 balances with the 3/4 r. Okay, so now it's just a case of substituting for r, and we are, well, we've got to substitute for r, and then we're all okay. What I'm going to do is substitute for r from this one into this one, I think. So we've got r is equal to 4/3 T cos 20. So sub for r, we have 4/3 T cos 20 plus T sine 20 equals to 40 G. And I'm going to times by 3. So we've got 4T cos 20 plus 3T sine 20 equals to 120 G. So I don't get any stacked fractions. Factorise. 4 cos 20 plus 3 sine 20 equals 120 G. So the exact answer is T is equal to 120 G over 4 cos 20 plus 3 sine 20. But this is M1. You're not going to get marks for an exact answer like that. Work it out. 2 or 3 significant figures. 2, 4, 6 newtons. Okay, so fairly standard first question as it should be. Let's have a look at question 2. Okay, so here we have a moments question. We're told that something's being in equilibrium, and we're also, one thing I always check out for, it's a uniform rod, so that's important. We've got a buoy of weight 400 Newton up B. Of course, we're going to have different reactions, which is what we're being asked for. That's RD and RC. And it's uniform, so we've got a weight in the middle, acting in the middle there. It's 3 meters, so it's on either side 1080 newtons. Well, we're going to, I suppose we're going to need to take moments about somewhere. We could take moments about C and D, or either one. If I take moments about C, I'll get MD, but then I can easily work out RD, but I can easily work out RC as well. So moments about C, I would get this distance here, which is going to be 3 times by 3 minus 0.5, so that's 2.5, times by 1080, so that's 1080 times 2.5. Also going clockwise is this distance here. That there is 5.5. That's 5.5 times 400. 400 times 5.5. To be consistent with how I'm setting out. And that's equal to RD. That distance from there to there is 3.5 because it's 2, 0.5, so it's 6 minus 2 minus 0.5, so that's 3.5. That gives me RD, 3.5 RD equals to 4,900 newtons. So RD equals to 1,400 newtons. Right, okay, well we thought work out RD first, but it's easy to work out the other one because I would, rather than take moments again, it's normally easier to just do forces up equals forces down. RC plus RD is equal to 1080 plus 400, 1480, but RD is equal to 1400, so RC is equal to 80 newtons. Okay, so that's the first question, part A, done. Now let's have a look at part B. The buoy now stands at point E, where AE equals X, and the girder remains horizontal in equilibrium, given that the magnitude of the reaction at D is now 520 greater. Okay, let's draw the diagram again. So at some point, let's call some point here which we'll call E. Buoy is now here, 400. And now we're told the reaction, how they vary to each other. We're told that the reaction here is 520 more than it is here. So let's call it R plus 520 compared to that R there. And we've got the weight again acting in the centre because it's a uniform rod. Right, okay, and so that's A, that's E, and it wants the distance AE, which I'll mark on as X on my diagram. Okay, well again, just like the last question, it's going to be much easier to work out R first, so by resolving vertically. So we've got R plus 520 is equal to 1080 plus 400. So that's going to give us 2R equals to 1480 minus 520, so that's equal to 960. So R equals to 480 newtons. Right, okay, so we then need to take moments. I'm going to take moments about A. I know it involves an extra force. Often we normally take moments about a support or about where a string acts, if it's that type of question. But I'm going to do it about A because that's going to mean that even though I've got 4 forces and there an extra force, the X is nicer. I don't have to bracket anything or to expand any brackets or anything like that. So I'm going to take moments about A. But of course you can take about either of these 2 points, which doesn't make much difference, to be honest. Anyway, so we've got horizontal. We've got clockwise these two are going clockwise. Okay, they're going clockwise. The 1080 and the 400 newtons. And if we mark some distances on, this distance here, as we've seen, is 0.5. That's AC. This distance, because it's a uniform rod, is 3. That's what we've called X, of course. And that distance there is 4 take away 2, which is 4. So that should make it easier to set up our moments equation. So we have R 3 times 1080, 1080 force times distance, 1080 times 3, of course it doesn't matter, I'm just trying to be consistent with the order, times 3, plus 400 x, that's the distance we want to know, is equal to, and the two clockwise ones, R, which is 480, times by 0.5, plus this force here, which is 480 plus 520, which is 1000, times by 4. Okay, so that's going to give us, when I work all that out, it's 400x equals to, when I multiply that out and rearrange, that's going to come to 1000. So x is 2.5. Okay, so that's question 2. And I'll put the units in there, 2.5 meters, but there we go. I think that's all done. Question 2 is done. Let's move on to question 3. Okay, so we've got impulse equation and momentum we need to use. We've got particles P and Q are moving towards each other. P has got mass 4m and it's moving with velocity 2u, and Q has got mass m and it's moving with velocity 4u. Okay, now we're told that on impact they kind of join together. You know, that they actually join, the word coalesce is sometimes used, or they've just described it as being joined together here. And after that point where they join together, of course they're going to go with velocity out that way. I know it's going to be that way because the momentum is positive when in that direction. The momentum of this is greater than the momentum of this. So if they join together, they'd have to go that way. So let's apply the conservation of linear momentum equation. Mass times velocity, so it's 4m times 2u minus, because it's going in the opposite direction, m times 4u is equal to, now of course if these join together we can regard that as a single particle of mass 5, m times v. Now m cancels, so that becomes 8u minus 4u, so that's 4u equals 5v. So v is equal to 4 over 5u. It hasn't asked for that, but we need it to work out the impulse. Now to work out the impulse, we need to look at what's happening on each of these particles during the impact. We've got an impulse on that one at the point where when it's changing velocity in that direction, kind of going to the left, and we've got an impulse on Q going in that direction as they join. So I'm going to apply it to Q because it's then everything, then I can just regard positive in this direction here. Okay, so the impulse is equal to m final velocity take away initial velocity, and as always with impulse and momentum, got to be very careful with signs. Now the mass of this one is m. The final velocity is positive because it is going in 4 over 5u. Now it has started off going, because we're doing on Q, so we're doing on Q. You can do it on P as well, but It looks easier to me to do on Q. On Q, this is going in the opposite direction, so let's take away a negative of 4u, or positive, just add the two together basically. Okay, so then that, when we put an overcommon denominator, that's 20u plus 4, so that's 24 over 5 mu. And that's question 3 done. Okay, let's look at question 4. So question 4 is a forces question, resultant of forces. Must be careful with these questions to read carefully what's going on, because we've got a force F1 which is due east of 8 newtons, but we've got the resultant which is going of that under force F2, which is 14 newtons, which is going in that direction. So obviously F2 must be coming off there somehow, because it's the result. So it's asking for the magnitude of F2 and the angle that F2 is making as a bearing. This angle here is obviously 30 degrees because we've got a bearing of 120 from the north clockwise, 120 degrees there. Okay, so let's do the diagram, because this, I'm going to draw a vector triangle, so we can work these things out. It's going to be cosine rule and sine rule and that type of thing. Okay, so we've got 8 newtons in that direction, and then we've got the F2 is going off like that. A bit wobbly, never mind. I'll put my pen there, F2, and we're told the resultant here is of 14 newtons. And we know that this angle is 30 degrees there because, as I said before, the bearing is 120 degrees. So there's our vector triangle. So to work out the magnitude of F, again, we're just going to use the cosine rule. Magnitude of F2 is equal to these two angles squared and added. It's not angles, sides, lengths, 8 squared plus 14 squared. Take away 2 times 8 times 14, cos 30 degrees. Okay, and that gives me F2 squared, so F2 squared is equal to 66.0 and some of that stuff. So taking the square root of that, F2 is equal to 8.12 newtons. Now, as usual, be careful with rounding here. It is 8.12 newtons to 3 significant figures, but I've stored the number in my calculator because we're going to use that in the next part. Its full display is 8.124672889, but I've stored that in the calculator, and so that I'm not going to get around in error. So if you don't know how to use the store on your calculator, learn it, because it's in mechanics it's quite important, and in maths in general. Just avoids writing the numbers down, and it just makes life a lot easier. So yeah, so we need to work out the bearing that F2 is going on, but in order to do that we certainly need this angle here, theta. Once we've done that we can convert it to a bearing, but let's work that angle theta out first, and we're going to use the sine rule now, and we can say that sine theta over the side opposite equals, now we've got the 30 degrees over F2, sine 30 degrees over F2, which is 8.12, but as I say, I'm going to actually put in the stored number that I have on my calculator there. Okay, so that gives me, when I work out sine theta, I get 0.86 0.615. Okay, so when we inverse sine that, the principal value is 59.5 approximately. But we've got to be careful because this is one of the cases of the ambiguous case, because the angle that we're looking for is definitely obtuse, otherwise you wouldn't be able to draw this triangle with an 8. You can check afterwards if you like, but you wouldn't be able to draw a triangle if you used the acute angle. So the actual angle we want is 180, take away this number that you get, theta equals the arc sine of that. And say look it up, it's covered at GCSE as well. It's called the ambiguous case for the sine rule. It actually occurs whenever, if ever you use the sine rule and the angle you find is bigger than the one that you're given, then that's called the ambiguous case. So that gives us theta equals to 121 degrees. Okay, it's a good job that I've used the exact and the larger thing and used the memory, because the actual number I'm getting here is 120.50632226. So it would be easy if you're sloppy to get 120, to get a number that rounded to 120 degrees there. Anyway, we're not out of the woods yet, because we want the bearing, which is from the north clockwise, as I've marked on this diagram here. Okay, so it's from the north clockwise. So that will be, because this angle all the way around here is 270. So the bearing is 270 degrees, take away 121 degrees, which is equal to 149 degrees, to the nearest whole number. Okay, so a little bit tricky, this ambiguous case thing here, but we can see it has to be an obtuse triangle. The other triangle if you work out the 59 degree angle, that's basically, if we draw the case here, it is basically a case where we've got if we talk about the F2 there and the 14 there and the 8 here, the other angle of 52 would be if we've got this, which of course wouldn't be possible because we need to have that to be 8 from there to there. So ambiguous case, have a look at it. If you're unsure, check out ambiguous case to see why it's the obtuse angle. Okay, so that's that question done. Let's have a look at question 5. Okay, so we've got a vertical motion question. We've got a ball being hurled up from 2.5 meters and then hurled upwards with a velocity of 14.7 meters per second. Upwards, and we're being asked for a few things. First thing is the maximum height, so we're being asked for that height basically. Well, let's just work out this height first and just add on the 2.5. So we've got the initial velocity upwards, we're taking upwards as positive, is 14.7. Acceleration, because we're taking upwards as positive, is minus g, minus 9.8. When it reaches the top, v equals 0, and we want to find s. So we're going to use v squared equals u squared plus 2as. So that gives us 0 squared is equal to 14.7 squared plus 2 times minus 9.8 times s. So that gives us s is equal to 14.7 squared over 19.6, which when we work that out comes to 11.025. But we need to add on, so the height h will be added on 2.5 to that. So if we give three significant figures, that's 13.5 meters. Okay, so then it says the time taken for the ball to reach a height of 1 meter above the ground. Now this is the ground here. Okay, let's take that H off. So we want it, the time, we know that this is 2.5, so we've been asked for the time when it goes from here upwards down to here. Well, the key here is if we take this as our zero displacement point, displacement when it's 1 meter above the ground, if we're taking that as our 0 point, is minus 1.5, say, not minus 2.5, minus 1.5. Taking that as our 0 point, and once we've done that, should be fine. So we've got B. Again, the initial speed is 14.7, or velocity upwards, 14.7. We want the displacement to be minus 1.5, i.e. 1.5 below the point of prediction, because it's 1 meter above the ground. Then we've got A again, because we're taking upwards as positive. A is equal to minus 9.8, minus G. And we're working out T. Okay, so there, if we put that into S is equal to UT plus half AT squared. We have minus 1.5 is equal to UT, so that's 14.7T, plus a half times minus 9.8 T squared. Rewriting that as the quadratic, well, just simplifying it so we can use the formula, 4.9 T squared minus 14.7T. And then minus 1.5 equals 0. Putting that into the quadratic formula, we get T is equal to 14.7, and it will be plus or minus. It will actually be the positive one we're taking, because the negative one will come out negative, so it would be the plus we're taking. That's 14.7 squared minus 4 times 4.9 times minus 1.5, B squared minus 4AC, over 9.8, because that's 2 times 4.9. And when we work that out, to say we get a negative answer, which we can ignore, and we get T is equal to 3.1 seconds. Okay, so one part to come now. The speed of the ball at the instant it strikes the ground. So we want the speed it hits the ground there. So now we're going to take displacement as minus 2.5, because we want the speed it hit when it hits the ground there. And we've got A is equal to minus 9.8. S equals that. U is equal to 14.7. And V equals to question mark. Now, we can say V squared equals to 14.7 squared, because we're using V squared is equal to U squared plus 2AS. 14.7 squared plus 2 times minus 9.8, but this is negative 2, so that's negative 2.5, not negative 2, negative 2.5, because they're both negative, so they're going to cancel each other out. So that gives us V squared is equal to 265.09. Taking the square root of that, we get 16.3. Now let's look at the question. It asks for the speed, so we want a positive answer. If it asks for the velocity, taking upwards as positive, we could say that it's negative, but it's asked for the speed, as it will normally do, 16.3 meters per second, but it's going in the opposite direction. So I have to be careful with signs there. because we had a double negative acceleration and negative displacement, which cancel each other out to make a positive in the equation here. Okay, let's have a look at the next question. Okay, so here we have a speed time graph question. We've seen something similar to this before, I think 2015 or so. It's a bit of an unusual one. It's told us the speed it gets to at the top, but then you have to set up this quadratic equation v. I say I have seen this before, this type of thing before, somewhere relatively recently. Now let's do this speed time graph. We're told that an athlete runs on straight horizontal ground, starting from rest, accelerates to a speed v. There. Then maintains this speed v for a certain period of time, which is not told, and then decelerates at 0.2 meters per second. So in other words, somewhat to reduce rate and just increase it like that. Okay, let's make it a bit more. There we go. It's obviously slowing down, but not at quite the same rate here as the speed, not 3 times less, in fact. Okay, so there's our speed time graph. What else do we? Pretty well all we need on here. I mean, we could put we really should put the 270 there. But that's pretty much all the information we're directly given, so the marks should come just from that. But I'm going to, for the next part of the question, it might be useful if I call this time t1 and this time t2, and therefore the time from here to here is 270 minus t1 minus t2. Right, so it says so that she accelerates for 5v over 3 seconds. Well, the gradient equals to acceleration. So that tells us that v over t1 is equal to 0.6. which is equal to 3 over 5. So that, rearranging that, let's write it out separately, 3 over 5. So rearranging that, we get v is equal to 3 over 5 t1, which of course gives us t1 is equal to 5v over 3 as required. That's what we asked to show there. So make it clear that we know that that's what we've done for part B. And then it talks about the setting up a quadratic equation. Now we need to do something similar for T2. So again, gradient equals acceleration. We need T2, and then we're going to use the areas. So T2 V over T2 is equal to 0.2. Now you could say, well, it's accelerating, so shouldn't it be negative? Well, yeah, but in that case both are negative, so we'd have a negative there and a negative there. So there we go. Don't need to bother with that. It's just basically the ratio of this to this has to be 5 to 1. This length here has got to be 5 times this length here. So that gives us that V over T2 equals 1 over 5. So V is equal to, sorry, T2 is equal to 5V. Okay, so now it's a case of now it's a case of just setting up our quadratic equation. Area equals to distance. Area under equals to distance. So we've got half times V times T1, that's this triangle here, plus And now the time here is this bit here, that's 270 minus T1 minus T2, but that's a rectangle times V. And then that's this triangle here will be half V times T2. And that equals to, it tells us the distance it travels, which is 1,500 meters. Okay, so now we can just put in the values for t, and hopefully we'll get the kind of quadratic they're looking for of that form. Okay, so we have a half times v times t1, which is 5v over 3, plus 270, take away t1, which is 5v over 3, take away T2, which is 5v times v, plus a half times v times T2, which is equal to 5v, is equal to 1,500. Let's multiply this out then. We have, that's 5 over 6v squared, plus 270v, take away 5v over 3 squared, take away 5v squared, plus 5 over 2v squared is equal to 1,500. So now I'm going to times by 6, just to get rid of the fraction. So we've got 5v squared there. This bit here will be 1,620v. This will be equal to 10v squared. This bit will be equal to 30v squared. This bit here will be equal to 15v squared. And then 1,500 times by 6 is equal to 9,000. Now rearranging that, we get 20v squared minus 1620v plus 9,000 equals to 0. Let's divide by 20 now. V squared minus 81v plus 450 equals 0. Okay, so that does look to be very promising because it's of the form they want. And then it says find v. So this is a quadratic which factorizes. You might think, oh, I can't factorize that, but really there's got to be two negatives here, so we're just looking for factors of 450. And if you start with 150 and 3, and then 70, doesn't take too long, 75 and 6. So we've got v equals 75 or v equals 6. Now it says justify your answer. V equals 75. It was okay to say it's just unrealistic. We're talking about a runner here. That is just far too fast. That's okay. If you look at it, you could, there's other things you might observe here that there's no way that you could have fitted into. We could have had v here. This would have been negative for t3 for this time here. So, but anyway, it's unrealistic, and that's enough of that. So v equals to 6 is the answer. Okay. So one more question to go. Okay, so we've got a dynamics connected particles question. The first thing is to write down equations of motion, so apply an F equals ma. Let's put some forces into our diagram here. Oh, that doesn't look very straight down, does it? That's a bit better. So we've got 3 mg downwards, r, and let's see what it said. It tells us that the coefficient, we've got friction, which is a quarter r, so we've got friction going down. Well, which way is it going to go? Actually, it's going to obviously go this way, so friction will be moving in this direction here. Mu r is we're told it's a quarter, so that's a quarter r down the slope. We've got a tension here and a tension here, and we've got a 4 mg here, and it's going to be accelerating in this direction. Okay, so So there's our diagram, and we're just going to apply for part A. We as always through these questions, we apply F equals ma to each individual particle. So for this one here, that's easy. We've got 4mg going downwards. T going upwards is equal to 4ma. For the particle A, we've got going upwards is T, but we've also got the component of the weight and the friction. Now the component of the weight going down the plane here is 3m, it's this component here because we've got an angle which we can mark alpha there, and because it's away from that angle it's 3mg sine alpha. Down the plane is the component of that weight. So completing the equation, minus a quarter r, take away 3mg sine alpha is equal to 3ma. Okay, now we can say, because we're told that tan alpha is 3/4, we can say that sine alpha is 3/5 because of the 3, 4, 5 triangle, or you can get it from your calculator easy enough as well. So sine alpha is 3/5 and cos alpha is 4/5. Okay, so well, we don't know what r is, but we can resolve perpendicularly because there is no motion in this direction. So the forces have to be balanced perpendicularly. So we can resolve perpendicular to the plane, and we get r, and again this component now, that's there, is 3mg cos alpha. And we know that cos alpha equals 4/5, so r is equal to 12 mg/5. Okay, so we can now put all of this into, we can sub these into this equation. So we've got t, take away a quarter times 12 mg/5, take away 3mg times sine alpha, which is equal to 3/5, is equal to 3ma. So we've probably already got the answers for A, by the way, and we're now doing part B. That was definitely enough to get the answer for part A. They kind of merged into the two here. So, okay, so that there will give me T. Let's tidy this up before we do anything. That's equal to T times 3mg/5. Take away 9mg/5 is equal to 3ma. So that gives me T minus 12mg/5 is equal to 3ma. So I'm going to add these two together, as we often do in these types of questions, to eliminate T. So add, I get 4mg. Now the T cancels, minus T plus T. Take away 12mg/5 is equal to 4ma plus 3ma, so that's 7ma. Okay, now obviously m cancels, and putting this in a common denominator, it's 20/5 minus 12/5, so it's 8g/5 is equal to 7ma. This was a so that question, which is quite reassuring because it did say so that it's 8/35. So I've still written the m in there, of course. So that's A is equal to 8/35g. Right, so that's part C done. On part B. C, it says explain, this is a little 1 mark question, how you've used the fact that the string is inextensible. It's one of these modelling things. If it wasn't inextensible, you know, it could be moving and kind of, it would be elastic string. and then they wouldn't necessarily have the same acceleration. So the answer here really is only this: acceleration is the same. Okay, so now we have a long 7-mark question at the end. Fairly common scenario. B hits the ground, and then A carries on moving up the slope, and how far is the total distance it travels? Well, there's a few things we need to work out. We need to work out the speed of A and B, of course, speed of A and B when B hits ground. So that's during the accelerating phase, because it's going to be accelerating at that point. So to do that, well, we know the acceleration. That's from what we worked out before. That's the 8/35g. We know that the initial velocity, because it's released from rest, is 0, and we know we want to work out v, and we also know that it's moved 1.75, so s is 7/4, 1.75. So we can use v squared equals u squared plus 2as to work out the new velocity. So that's v squared is equal to u squared, which is 0 squared, plus 2 times a, which is 8/35g, times by 7/4, which is the distance. So that gives me, because that's 16/4, so it's 4. The 7 cancels with the 35, so that works out as v is equal to the square root of 4/5g. I'm not going to bother working it out because it's not required. We can use that exact answer in our further calculation. So that's one thing we need to work out. We then need, because then when the string breaks, we need to work out the new deceleration, because there'll be no tension at that point. So basically at that point we're going to have something moving, and we're going to have friction, a component of weight. R is still going to be equal to 3mg cos alpha, which is equal to 12mg/5. R won't change. R will still be that from the resolving equation. Mu is still equal to, we were given mu equal to 1/4, but we need to apply F equals ma to work out the new deceleration. So F equals ma. So that gives us the friction, because of course it's moving in this direction, so minus 1/4 R is the friction, but we know that R is 12mg/5. Take away the component of the rate, which is equal to mg sine alpha, is equal to ma, but of course we've got a 3 here, because it's 3mg here. So that equals to 3ma. Okay, so that gives us that minus 1/4 times by 12mg/5 minus 3mg times by 3/5 is equal to 3ma. M cancels again. So let's just work this out. Then we have, that's 1/4, so that's minus 3/5g minus 9/5g is equal to 3a. So that gives us 3a is equal to minus 12/5g. So A is minus 4 over 5g. Okay, so that's the deceleration when I said string breaks, but it doesn't break, does it? When B hits floor. Sorry about that. Sometimes you're told it breaks, but this time it's B hits floor. So we've got, basically what's happened is this part, going back to the diagram, this has hit the floor, A is now decelerating with this deceleration with this initial velocity. So now what we want to find out is the extra distance that A moves whilst decelerating. Because it doesn't just suddenly stop, of course. Decelerating. So that gives us, we know that U is equal to velocity attained whilst it was accelerating when the string was still tight. That. We want the distance it has when it comes to rest, which is V equals 0. It's decelerating with this that we found here, this minus 4 over 5g. And then we want to work out the distance it moves. So we use V squared equals U squared plus 2AS. So that's 0 squared is equal to U squared, which is 4 over this squared, which is 4 over 5g, plus 2 times by minus 4 over 5g times by s. Now clearly here g cancels, and in fact what we end up with is 8 over 5 s is equal to 4 over 5, so s is equal to 0.5. But do answer the question. It's quite a common one. If people have done so much work, often don't answer the question. It says find the distance travelled away from the instant when it's released. Well, it will have already moved 1.75 meters upwards when it was, so then it's gone an extra whilst it was accelerating, and then it's gone this extra 0.5. So the total distance is equal to the 1.75 plus 0.5, which is equal to 2.25 meters. And that's it. Paper finished last October 2017 IAL. Hope you found it useful. Bye.